Is it rolling?
Hi, Theo.
All right, let's go, people. Only 3 of you are here. The other of you, the rest of you are taking your English clausur. We have a visitor. Lovely. Thank you very much for being here. We're going to talk about gravity, wrapping things up today. We've got, I think, 3 or 4 things left to do in terms of gravity. The first one of those was regarding orbits. We talked about that yesterday. We have the Earth or a central mass, and we have an object orbiting here. We talked about the speed of the object orbiting, okay? And we derived the equation for that super quickly. We can do it again, not difficult. The force acting on the orbiting object is gravitational force. Exactly, with gravitational force acting on the orbiting object, that's Fg, okay? That is the force that's pushing this thing towards the center. This has mass, little m. What is that force doing? Attraction. It isn't attraction, but what is the effect of a force?
It makes it like spin around it.
Okay, that's the technical term. Thank you very much. Viola, what's the effect that force has on objects? It's causing acceleration. What kind of acceleration do we have here? Centripetal acceleration. Very good. So we have centripetal acceleration. So we have Fg equals mac. That's the basic idea. And we put in the universal law of gravitation, right? For Fg, we have big M g over r squared, where r is the radius of this thing. Okay? And on the right side, we have m times ac. What's the equation for centripetal acceleration? Starts with v squared, ends with over r?
V squared over r.
Good job, team. Very, very good. You're brilliant. That's why I keep you around. So v squared over r, we can cancel out something here. What can we cancel out? M would work. Good job. That's one thing. What else can we cancel out? Let's do green. Yeah? R. That's schön. There we go. Cancel out one of the r's. There we go. And we have, of course, here the orbital velocity. We have this result, therefore, that the orbital velocity is equal to the square root of mg over r. Now, there we go. We could also, from here now, think about the energy that this orbiting object has. Okay? As the satellite, ISS, whatever, orbits the Earth, what kinds of energies does it have? One? Kinetic energy. Good. So it has kinetic energy. So overall energy is kinetic energy plus potential. What kind of potential?
U.
U is the letter. What's the subscript?
G.
G for gravitational. Very good. So we got gravitational potential energy. Total energy for the orbiting satellite is kinetic energy plus UG. Equation for kinetic energy.
1/2 mv squared.
Isn't that?
Oh wait.
Oh wait, no. 1/2 mv.
It is 1/2 mv squared. So we got that equation. Cool. So we've got 1/2 mvo squared. This is an O, not a 0. So this is not the initial velocity. This is the orbital velocity. What do we have for UG? What's the equation for UG? Anybody remember? We had that. Yes?
mg changing h.
Okay, so we have for a object near the surface of the Earth, that's the correct equation. Delta UG, right? Delta UG is equal to mg delta h when we're looking at an object that is over a small delta h. And I'm being very generous in my interpretation of a small delta h because obviously this would be like 600 kilometers or something like that based on that scale. But the general equation for gravitational potential energy, yeah.
Is the other one. With
Good.
The
What you got?
large G
Yeah,
and M1, M2 over R.
good. And the very important thing here is a minus sign. So we've -1 is because gravitational potential energy is always negative. We define gravitational potential energy of two objects to be 0 when they're infinitely far away, Therefore, if they're not infinitely far away, any closer situation, they are having negative gravitational potential energy because you would have to do work to move them apart. To get them to gravitational energy of 0, you'd have to, you don't have to make that noise, but it works, push them apart, infinitely far apart, and then they would have gravitational potential energy. Another way of thinking about that idea, this equation is, if you think about a graph of this, UG versus R, kind of looks like that, right? So wherever it is, like here, to get it away, you'd have to push it uphill. That's a good analogy to think about it. So you need to do work to get it away from each other. You have to give it energy to get it to 0 energy, so it has negative energy.
Why do we want it to have 0 energy though? Why would we push it?
We wouldn't want, but for example, well, sometimes we do want it to have 0 energy. Example, not to bum you out, but you know, this is the place you're born, this is the place you're gonna die. Some people are bummed out about that. They're like, I'd really like to escape this rock, right? I'd like to get away from this earth. And in order to get away from this earth, right, you'd have to move your body away in a spaceship, which means you have to give it energy to get to 0 energy when you're freed of the gravitational well of the earth. And the gravitational well of the sun if you want to go actually leave our solar system, but that's like even a step further. Let's just go to the moon is hard enough. But getting away from our solar system would be another step. Okay? Making sense?
Yeah.
Cool. So if we now put that equation in here, some interesting stuff happens, and I hope you get geeked out. We're going to put that equation in here first of all. So we have minus mg over r. And now we're going to substitute in for the kinetic energy for v orbital because we have that equation right here. We're going to plop that in here, and we're going to get 1/2 m. Let's take a look. Square root of that is,
mg over r.
mg over r. mg over r. And then we take this, we subtract minus mg over r. Something interesting happens for the total energy of an object in orbit. Can we combine these two terms? Yeah. What is it? You know?
Negative 1/2
Mhm.
m, lowercase m, capital M,
Great.
g over r.
It's negative 1/2 mmg over r. That's cool. And of course, I don't know if you noticed that, and that's one of the reasons why this is super geeky. Well, that's negative this. Well, that's that. Well, that was that. Well, that's just this. So the total energy that an object in orbit has is actually equal to minus k. It kind of, I know that kind of blows your mind or whatever, but it has kinetic energy. It also has negative gravitational potential energy, right? And the negative gravitational potential energy is actually equal to, the negative gravitational potential energy is equal to, okay, let's try this again. So you have kinetic energy, and then the negative gravitational potential energy is equal to, okay, I'll try that again. So you have kinetic energy,
We really need a 12th grader to share this.
and the negative gravitational potential energy.
AJ, help.
Okay. You go one step over for the kinetic energy, that's positive energy, you're like, yay! But in order for our total energy to be negative k, even though we did plus k, we got energy. Now gravitational potential energy not only gets us back to 0, gets us to negative k, so that means that the gravitational potential energy is actually equal to minus 2k.
Got it.
Right? So UG is equal to minus 2k. That's fascinating. I don't know if that's fascinating to you. You can look at it that way. You can look at it like this way. That's interesting. Like, all right, that's pretty cool. Or you can think about it, okay, is equal to minus UG over 2. That works too, right? You can solve that for k. I don't know. Those are just kind of relationships there. But the key thing is, key facts here, total kinetic energy, the kinetic energy is in magnitude, half of the magnitude of the gravitational potential energy in the orbit. Of course, when you're in orbit, you are still captured by the gravitational well that you're living in. The Earth owns you, or the sun, or whatever. You would have to climb out to get away. So you have to have negative energy, and the amount of energy you have is actually equal to negative K. Capiche, capash? Capuche? Okay, now just a reminder that this thing, the sum of these two things in this class, we call this mechanical energy. And we add to that spring potential energy, but surprise, surprise, planets and moons are not attached to springs, so we don't have to worry about spring potential energy. So we talk about the total mechanical energy of the moon, or the total mechanical energy of the Earth in this case. Cool? Making sense so far? Cool. Let's stop the video now and let's restart it so we can kind of clip it a little bit. I know I could do this like electronically, but that way also if something fails,